All right, line P1, learning task number 5. We're going to take a look at transformer polarity and marking for transformers. The first thing that we need to say is that transformers are only an AC type of component. And we know that when it comes to AC, we are going to go and have both a positive and a negative going waveform, right? Which means that we don't have polarity in the same way that we were used to when we were looking at a DC type of component. On a DC type of component, let's go with a battery over here, we knew that we could go and take a look at one end of the battery, and this thing would be positive, this end over here would be negative. Always, right? Based upon the way that the charge separator that we're going to go and have inside of there is going to go and move electrons, out from one end of the battery to the other. We don't have that when we are dealing with AC. What we do have is we have got what's referred to as instantaneous transformer polarity. We want to go and be very clear that this instantaneous value is what we're looking at. In other words, it is going to be at any instant. If we freeze time, we should be able to go and tell a transformer polarity. If I would freeze time right over here, I would see that this waveform is currently positive. And if I were to examine any other waveforms at the same time, I would be able to, if I froze everything at the same time, tell if they were going to be positive or negative in relationship to this one as well. All right, let's go and take a look at how we're going to go and use these. First of all, we do have the markings. We've already talked about that high voltage windings are going to be marked with H's and low voltage windings are going to be marked with X's inside of it. We need to know, once we have got high and low marked, how we're going to mark everything else. Now, if I've got an unmarked transformer, I have to start by always identifying the H1 lead. The H1 lead is always going to go and be a constant. And the way that I determine where my H1 lead is going to be is I walk myself around to the low voltage side of the transformer. So I'll literally just walk myself right over here. And then if I'm over here, what I see across the transformer and on my upper left will always be the H1 that I'm going to go and have. Same with that if I were to walk myself over here. Upper left is going to be my H1. What's even better is, hold on a second, if my transformer is a step-down type of application, my H1 stays in the same position. Okay, step-down application is where I'm going to go from step-up application, where I'm going to go from low voltage over to high. What I'm always going to do, even if I've got a transformer where the highs are drawn on the bottom, is I'm going to walk around to this side of the transformer, and then standing on that side of the transformer, look across to the left. So this one would be the H1. We always start anything to do with transformers by establishing where the H1 is. If I have not established the H1, I cannot do any further analysis for my polarity that I'm going to go and have on my transformers. We need to have this because there's a bunch of things that require knowing what the instantaneous polarity is going to be. Paralleling transformers, if I do that improperly, if I don't know my polarity, I'm going to go and have short circuits. If I'm connecting three-phase transformer banks in third year, if I don't get this now, I'm going to be expected to know it by third year, and I'm going to have huge troubles trying to make those. If I'm connecting metering and protective relaying, if I need to measure something, I need to know what my polarities are going to go and be. Let's start with additive versus subtractive polarity. We have two main types of transformers, additive and subtractive types of transformers. You'll note that the high voltage side, H1, is always a constant. I see that from my H1, I go across to the opposite side of that winding, which is going to be my H2. Then if I take a look, it is the relationship between the H1 and the X1 that is going to go and determine whether something is going to be additive or subtractive. And really where it's getting this whole additive or subtractive thing is always going to be based upon some autotransformer action. We're going to examine that later on and talk about why these are called additive and subtractive, but that's not for another couple of learning tests till we're into our autotransformers. How do I keep them apart? Memory tricks. I need memory tricks for absolutely everything. What do I know about an addition sign, the plus sign? I know that a plus sign crosses over itself, right? That's a poorly drawn one there, but it's a plus sign. It crosses over itself. I know that an additive type of transformer crosses over the core. That's how I keep these things just straight in my mind. It does not matter whether you use additive polarity versus subtractive polarity. You can use either. You can even mix them inside of a system as long as you make your connections correctly. There's nothing that's going to be like more efficient from one versus the other or anything like that. They are standardized. My subtractive polarity is usually going to be for my generation, like inside of a hydroelectric dam, and where I'm stepping back down again inside of a switchyard. You know, we're talking hydro type of stuff right now. It's generally going to be additive polarity for distribution. We work more with the distribution than we do with the power transformers. But it could be really either one of those. We also have got another class of transformers that we're going to examine in depth later on, which is going to be my instrument transformers. And instrument transformers oftentimes don't even have H and X markings. They might have just like a single H where they're going to go and have, you know, H and X, but it's not going to identify a specific terminal. What they do have is they've got dots, and those dots are going to go and indicate, once again, instantaneous polarity. What is instantaneous polarity? Instantaneous polarity simply means that my whatever voltage I'm putting in here right now, remember how it's AC, and it can go up and down, positive, negative? In other words, if I've got this attached to my AC supply, this H1, and if this is currently the positive and this is currently the negative, transformer polarity means my H1, my X1 is going to be the exact same. So at this instant, this would be positive, and therefore we can't have a positive without a negative. This one here would have to go and be my negative off of there. When my AC alternates, changes over to a negative, this other side of the AC would have to change to a positive, then this H1, my X1, is also going to do the same. It's going to go and match it, which would mean that this side over here would have to be my positive at that point. Okay? H1 and X1 always, always, always have the same instantaneous polarity. H1 is negative, X1 is negative. H1 is positive, X1 is positive. It doesn't matter whether we're looking at a subtractive polarity or whether we're looking at an additive polarity. We can do the exact same thing over here. Take an AC supply, drop that thing onto there. When I'm positive, negative like that, that would mean that I would be positive here. X1 follows the H1. And negative that I would have over here. And then when this alternates, negative, positive, when this becomes negative, and that becomes positive over there. All right? Keep that in mind. H1 and X1, the same, instantaneous. They won't be the same magnitude. One's high voltage, one's low voltage, but they're both going to be going positive or going negative at the same time. We should also talk about when we've got multi-coil. If we have got multi-coil transformers, we are going to go and have, it's going to look like this. See these later on. We'll draw a high voltage side, and we will draw a low voltage side. And then I'm just going to designate these ones. Once again, if this is my high voltage side, I'm going to walk myself over here. I'm going to go and look upper left corner, and I'm going to label that one H1. H1 will always terminate onto an H2. So this here would become an H2, and then I would loop to here. This is going to go and become an H3. Really, this is the H2. We just draw them crossed over like this. Later on, you'll see why that's convenient to draw them like that. And then this would be my H4. Over here on this one, let's say that we go additive. So if it's additive, it's going to cross over. And I'm going to have my X1 here. X1 travels through its windings to terminate onto X2. This one here becomes X3. This one here becomes my X4. If I have got transformer polarities, H1, whatever H1 has, I'm going to have the same for my H3. The odds are going to go and stay the same, which means that on this side over here, the odds are going to go and stay the same as well. Once again, if this thing was a positive over here, let's say that H1 was positive, then H3 would have to be positive, which would mean that this H1 would have to be positive and this X3 would have to be positive as well. Okay, if it's a multi-coil, just keep all the odds the same polarity, all the evens the same polarity as well. We've got two main methods to go and test for whether something is going to go and have a additive or subtractive polarity. If I don't know which one it's going to be, I'm going to have to do some testing. And the testing has got two main types. We've got the AC voltmeter test, which is really basically an auto transformer. We're going to take a look at this right now as a simple transformer, but later on we're going to go and deal with these in auto transformers. It is sometimes referred to as the auto transformer test. It doesn't matter which one you want to go and call it. Voltmeter test or auto transformer test. I get what's going on. We'll explain it over here. The other one that we less commonly are going to use is going to be the DC inductive kick test. That's going to be the next one. DC inductive kick test is going to go and require you to go and have two things that most of you don't have. You do need to go and have a DC supply. We don't have a lot of DC supplies that we carry around with us. You can use a battery, but it's limited. You're also going to go and need to have an analog meter. Most of us don't have an analog meter. You can buy a real cheap one for like $12. You can get like a Mastercraft one or something like that from Canadian Tire. But I don't know that I'd want to use one of those without worrying about that thing blowing up. So we're going to go back to this one over here, the AC voltmeter test, because this is what you'll probably most likely do. What we're going to do as well is we're going to go and unidentify these two over here. Because that's really what the test is. When I put those numbers in at the beginning, you're like, yeah, that makes sense. You know, I know what this thing is going to go and be. And I'm going to put in a value of voltage, a low value of voltage. It doesn't have to be the rated transformer value of voltage. This thing might be a 600 to 120 volts. 600 volts on the high side, 120 volts on the low side. What I can actually do with this test is I can go and place the low value of voltage on here, and then obviously I'm just going to get an even lower value of voltage out over here, right? It's 600 to 120, that's a 5-to-1 ratio, so I would get a fifth of the voltage out on the other side. I'm actually also going to go and remove this over here. We're going to start with this circuit in what we would refer to as the open configuration on both of these over here. So I'm going to start by standing on one side of my transformer. I've got an unmarked transformer. I don't know, somebody washed it or something. That'd be dumb, but whatever. It's unmarked. I've got an H1 over here. I look across the left-hand side. That's my H1. Once I've got that established, I call the other side H2, and then I'm going to go and place a test voltage onto that thing, a low value voltage onto here. I'm probably going to plug it into 120 volts because it's around, you know, and it's easy to go and pick up. So I'm going to place this thing onto 120 volts. I need to know what that test value of voltage is going to go and be. That test voltage is going to go and create some current, right? We know that there's going to have to be a little bit of current that's going to go and circulate inside of here, and that it's going to be setting up a counter EMF, which is going to be dropping that full 120 volts over top of here. Because there is current traveling through here, there's going to be some fluxing of my core. So we're going to have flux. That's going to go and flux our core generated across this side, where it is going to go and EG is equal to BLV. It's going to generate some value of voltage on there. We don't know what that value of voltage is yet that it's generating, but it's going to be generating something. Now, if this is a 120, 600, it's going to be 1/5 of that. So we're looking at 24 volts that it would be kicking out down over here. I think it's 24 volts. I don't know. I head math that. Maybe it's wrong. So there should be 24 volts that's going to be generated off of here. Ooh. I'm going to hide that one there again. If I have got 24 volts, it's going to be down here. What I see is I've got 120 volts. I've got a jumper going across here where I'm picking up one side of that 24 volts. This side stays open. And then I'm going to take that 24 volts and I'm going to go and pass over to here. Now what I'll do is I'll apply my voltmeter onto it. Good quality voltmeters should have a high impedance coil, so it's not like a short circuit or anything like that. I'm just measuring across here. If I were to go and measure 96 volts on here, that's going to go and indicate to me that this is going to be a subtractive transformer. If, same test over here, it's the same transformer over here, here's 24 volts, and on this one over here, now when I place my meter across it, I'm measuring 144 volts, that's going to become an additive transformer. And I can mark it as such, okay? So I've taken this, I see that I've got 144 volts, and I'm going to mark this thing as being additive. This one over here, I see that I've got 96. I'm going to mark it as being subtractive. It is always, always, always going to go and be whether or not this voltage is instantly adding to it or subtracting from it. This is vectors. This is where vectors actually come into play. Because over here, if we take a look, we've got an H1 and an H2 that are going to go and give me an instant value of voltage. And then I see that I've got another value of voltage that is going to be in opposition to it, right? If I take a look at X1 and H1, if they've got the same instantaneous value of voltage, it's like the arrowheads are on the same line, so they would be fighting against each other. I'll add them vectorially, tip to tail. My 120 volts plus 24 knocks me back down to a value of 96 volts. That's a subtractive transformer, and then I mark it as such. This one over here is an additive transformer because I've had that 120 volt vector and I've added in another 24 volt vector over there to get me to a grand total of 144 volts. The actual number that your meter spits out doesn't matter. It's just whether the number is going to be an addition of my source voltage. If it's my source voltage plus, this is going to be test plus, then it tells me that I'm dealing with an additive. In this case, whatever my test value of voltage is, minus, that tells me it's a subtractive transformer. That's how we do that test. So always start, make a complete circuit, feed in a low value of voltage onto here, and then when I go and take a measurement over here, if the measurement is smaller than what I'm feeding in, therefore, this one over here would have to be a subtractive. Whatever I'm connecting from one side to the other has got the same polarity. DC inductive kick test is a little bit harder to go and wrap your head around. You do have to go back into a little bit of basic induction from last week. It's not that far away. We shouldn't have forgotten it all yet. But we're going to go and take a current, and we are going to go and see a rise. Now, we know that if I take DC and I connect it to an inductor, I'm just going to block it out. Does this look like an inductor circuit? Have we done stuff like that before? Absolutely, we've done stuff like that before, where we said, look, that inductor is going to oppose a change in current. What's the current right now? It's 0 amps. When I go and apply this, we're going to go and see my current is going to go and rise to a steady state. And then once it's at a steady state, then it's no longer going to go and be changing, right? So from here on out, it's going to go and be steady at that point. So right now, for a brief instant, we're going to go and have change, and then steadiness. And this is going to be critical to understanding what's going on here. Well, how does that affect this side? That means that for a brief instant, when I power this thing up initially, I'm going to go and have an expanding amount of flux. My lines of flux that are going around here are going to be getting larger and larger and larger and pushing out, coming across to the other side of the transformer, thereby inducing voltage, right? Faraday's law, Eg is equal to VLV. We've got flux density, we've got conductor length, we've got velocity by the fact that this thing is moving over here. So we'll generate a value of voltage. Once we get to steady state current, this thing is going to go and have lines of flux that are stretched around it, but they're not moving, they're not contracting, they're not expanding. Therefore, what we have here on this side is no longer going to go and be affected. We don't generate anything on this side. We only generate on a transformer, when we feed DC into it, we only generate for 5 tau. Right? That's this over here. Probably draw tau like that, something like that. That's going to be the only time that I'm going to go and see anything across onto this side. So we're going to go and see generated action just for a split second. We do want to go and have our positive connected to the H1 and our negative connected to the H2. Okay, we need to make sure that we've got that. So once again, I would have started by walking myself over to one side of my transformer, standing on that side of the transformer, looking across, labeling that one as H1. Once I had an H1, H1 had to be positive. So that was how I started the test, is I made this circuit. You can do this off of like a car battery or something. You don't want to leave it in there for a long time. You don't want to use a toggle switch. You want to use something that's a push button. Just dump a bit of juice through and then pull that thing back off of it again. So this is positive, negative. On this other side over here, I'll erase myself. That was me standing sideways. I'm going to go and connect my voltmeter. Now your voltmeter does have 2 leads to it. Okay, where we're going to have a red lead to it. The red lead goes in the red socket on there. The black lead goes into the black socket on there. You mix up which one it is. They're always referring to what the socket is. You know, the rest of that is just your mistake. So we're just going to make the assumption from this point forward. You got the black lead in the black socket, the red lead inside of the red socket. The instant that we go and press this button, during that 5 tau, we're going to go and get induction that's going to go and happen, and we're going to get that mutual induction transformer action that's going to kick out to this over here. If my voltmeter moves upscale, in other words, the analog voltmeter, and we need to have an analog, digital ones don't really respond very well to this, but if this analog kicks upscale, like that, that would mean that this would have instantly had to have been positive, which would mean that this would have had to have been my X1 over here. If the instant that I go and turn this thing on, I see it pin, it kind of shake, you know, it pushes back up against the, there, it tries to go downscale, then I know that whatever it was reading had to have been a negative on this lead, which would mean that it couldn't be the same as H1. That would mean that this side over here would have had to be my X1. So all you have to do is just, it does not matter what your meter configuration is. You just go and take a look at your DC voltmeter over here, an analog DC voltmeter, whichever one is connected to this. If it kicks upscale, we mark that thing then as being an X1. If it kicks downscale, we mark it as being an L1. Once again, when we're doing our test, we're going to feed the value of voltage, even if it's a 12-volt battery that we're going to go and use. We're always going to feed it into the high voltage side so that whatever we're kicking out over here is going to be an even lower amount of voltage on the opposite side. There will be a kick that will happen when we open this up over here, because we've got all these lines of flux that are stretched out and around, and they're now going to collapse back inside. When they do collapse back inside, it's going to go and be, we're going to get that one over there, and so there is going to be cutting action again, and so my pointer is going to kick in the opposite direction. In other words, if I had this thing, when I first initially charge, I'm going to see a blip. It's going to go and push out like that, and then it's going to settle back in because we hit steady state current. And when we hit steady state current, we're not generating anything on this side. But then when I open this switch, then all of a sudden it's going to try to pin backwards down there. Don't look at the one when you're opening. It is always when you're closing in. All right, that's it for this one.